wrap up this problem that we were looking at last time. So I'll remind us, what we're staring at on the board is just a Bernoulli process. There's two things that come out. We've got a probability attached to it. And so we do this all the time with either ones or zeros right here, but we can also change that into indicators. Just think about two different things. What's the probability of saying one versus the other one? This is the fundamental setup to do any classification problem. So it's just comparing two things. And if you want to extend that idea to more things, this is just a tidbit, is you compare one thing against everything else. You do that for every category. So all those methods that are built up for classification are really just binomial problems in this sense. So being able to play around with binomial problems is the foundation. So I like this problem. This one's a little bit weird because it's asking me something I've never seen before in a real problem, where they ask you to estimate this shift. So what's theta? We want to know what that is. We're going to give you two data points right here. So you get cap x is equal to x1 and x2. Again, this is just a construction to highlight the difference between a confidence interval, or a confidence set in this case. The set, the 75% confidence set is this thing right here. We talked about that last time. So it's a statement about process. That I'm going to give you the correct answer. I'm going to cover the correct answer 75% of the time. Bless you. If you think I'm picking on my frequentist friends, I like being a frequentist too, it makes sense. And I think that it's a reasonable goal to try to be a frequentist. I would agree I presented this as a clumsy answer. So, and that's the whole point. So you probably want to say this is 50%. And that's 100%, but you need to condition on something. And you need a formal procedure for being able to derive answers like that. And that's very hard to do. So as a frequentist, so oftentimes they're giving you intervals that cover something. And this is the part where they're telling you, in general, it doesn't mean it's a belief statement about how much you believe that thing. And this is a good example to kind of untangle that. Because the normal example, when they used to tell us this, I don't think anybody got it. It's like, why can't I think of that interval? X bar plus or minus 2 standard errors, 1.96 standard errors. Why can't I think of that as a belief interval? What's the big deal? And a Bayesian does exactly think about that as a belief interval. I think the point is that this statement is sometimes misleading about what you think it means. So I'm giving that answer if that happens, and I'm saying 75%. And that's a statement about the process. If I keep doing that, even though that's right 50% of the time, and that's right 100% of the time on average, they're only right 75% of the time. So that's the distinguishing characteristic between the probability that you think that theta is some value and the confidence level. So the confidence statement is a statement about process. The Bayesian is going to do something different. So Bayesian always has two things. They've got likelihood. It's just two data points again. And they've got prior. At least kind of in this conceptual view of Bayes. All Bayesians have that somehow. What they're really doing is inference off of the posterior, and you operate through Bayes' rule to get there. I've seen other concoctions where people elicit posteriors and back out their priors. All kinds of weird things you can do with Bayes. So it's an operating system, and you can think about it different ways. So it's not always the case that you a priori have some insight. Oftentimes you write down the likelihood function, and you look at the nature of the parameters, and you want properties out of your posterior. So we wrote this down last time. This is, I should probably just start with proportional too, because it's a likelihood function. But I always do this. I given theta. Right here, this is a probability function. I'll put a 2 right here. So oftentimes I just interchange that f. I think last time I wrote PR. So you could do that. These are actual probabilities. And we wrote this thing down. Just this product. 1 to 2. And this was just 1/2 to the delta function that xi is equal to theta plus 1. And 1/2 delta function xi is equal to theta minus 1. So oftentimes we're trying to infer that thing, but we already know it. And the theta that we're talking about defines the restriction on what those points can be. So you need to put this in here. And I'm just going to say that xi is an element of two possible values, theta plus 1 and theta minus 1. And we spent a lot of time staring at this thing last time. Always happens. Every single time without fault. So I'm going to guess what's going to happen next year, my posterior predictive. We're going to spend a lot of time talking about that. But you'll never forget about this ever again. So always look at the boundary of the space. If the theta has something to do with defining the boundary of where the data can live, you will always need this indicator function in your likelihoods. It's a guarantee. So this part is just 1/2. That's always a half, no matter what. One of those two things happens. And so it's really just the product of these two indicators. And so this is just going to be delta xi is an element of theta plus 1, theta minus 1, and I've got two of these that I'm going to product together. I goes from 1 to 2. I'll write down proportional. So the likelihood function looks like that. And I'm going to rewrite it a little bit differently. I can write these indicator functions. I'm trying to write delta is my delta function. Sometimes I use a cap 1 or something like that. This is just 1 or 0 if the thing is true in the inside. And if it's not true, that's a 0. So I could rewrite this, that theta is an element of xi minus 1, xi plus 1. And you can convince yourself of that, bless you, just by examining these individual relationships, just inverting it and solving for the theta. So I like to think about it like that because I like to see my theta in one place so I can imagine what this function looks like. And it's just the product of these two things. So our likelihood function at the end of the day is just delta function. Theta is an element of x1 minus 1, x1 plus 1, times delta function. Theta is an element of x2 minus 1, x2 plus 1. Probably at this point of the game, after writing down the likelihood and thinking about it, understanding what these parameters mean, then I usually think about that. Or I can stare at this, and these really are encoding the same things. And I can say that's a shift parameter. And I have good reasons for not wanting to bury information in about the location itself. And so I'm going to use a flat chart. So I don't think you can just stare at this and say, what's the conjugate analysis? It's not going to work out here. So if I multiply by a flat prior here, the thing on the left-hand side won't be flat, it'll be point maxes. So that's not conjugate on its own. Remember how we got the flat prior out of the normal example? So we started with the conjugate prior, then we took a limit to come up with that rationale. So we're just doing that immediately and understanding that we want our prior maybe to be location invariant. So that's a property. We'll see how we do. And so I might pick this to be 1. So I'll just write down my reason. Location invariance. I think it's always important to have a reason for why you've done something. Somebody's going to ask you, and you need to answer back quickly. So, and I don't think an answer like, my teacher said to do it, is not going to instill a lot of confidence. But if you go, no, I took this class and I kicked butt, so I'm going to say confidently, it's a hard invariant prior. So for this problem, that just means location invariance. Let's look at the impact of everything. And just draw this out. There's 2 cases we need to study. So if I use the flat prior, my posterior is proportional to this. Two data points. And I'll write down proportionality. We'll normalize it after we draw it. So I would agree you're supposed to normalize it, but all the information is in the shape. So two cases. First case, x1 is equal to x2. I find it useful to give myself some numbers when I work through this. So let's just pick some numbers. I'm going to pick, say we know, I think I picked last time theta was 5, right? So let's just stick with that. So just say this was true. So I can have one of two values. These are either 4s or 6s. So I'm going to say maybe it's a 6. Arbitrarily, let's say it's 6. Just an example. Could have been 4s right there. And I just look at this function right here. And I think about what this is. So I've got right here, this is a 6. So this would be a 5 right here. And this would be a 7. Boom and boom. So if again, these are 6s, that's going to be a 5, and that's going to be a 7. So what this means is this takes on positive values when I see a 5 or a 7. This is a 1. When it's a 5 or a 7, it's a 0 everywhere else. Same thing twice. I can square that 1 all I want, raise it to as many powers if I keep seeing the same data point. I'm not really learning anything about this problem. And so I would end up with a 5 and a 7. And this would have some sort of mass right here. And if I were thinking about this actually as a density function, those masses would be infinitely high. And if I were thinking of this as measures, if I integrated then these things might just indicate 1s right here. And I might just say that's a 1. You can do it either way. I like to just think of them as just indicator functions. So typically, that would be a 1 from a likelihood function. So this is theta. And from that, I can multiply by my prior and come up with a posterior. And I can normalize it. Let's see if we can do that in our head. What would be the normalizing constant if this is the way I interpreted this? A half. So you can add a half twice, and it adds up to 1. So what we're going to do, if the prior is flat, so let's just say that's pi theta right here. It's just something, I guess it's flat here. That's where I should have drawn it. But I like drawing them low for some reason. No great reason to do that. We're going to normalize right here. And this will be my posterior distribution. This will be a half right here. And I'll have 2-point masses right at 5 and 7. This is the Bayesian answer, the posterior. It's always the Bayesian answer. And you might decide different ways to explain this answer. I would probably say 5 and 7, and I would agree my classical counterpart might say that. I think it should, and tell us what it all means, but you can get that from a Bayesian rationale. It's kind of just a kicker. And you can have it all right here. I can say this is what I believe, so my set that I would form would probably be those 2 points. You know, if I wanted a 100% set. You don't always want a 100% set if it covers the whole real number line, but you might want a 100% set in this case. You can basically say that has 50% probability and that has 50% probability. The nuance is, if I said this was a 50% probability thing, their paradigm isn't phrased that way. It's not the interpretation of confidence. And I agree, that's confusing. Like, what's this confidence thing? It's a probability statement about something, but it's not a probability statement about the parameter. And it can be elusive sometimes. So I would just report that back as an answer. And that's all there is to it. You could say, how am I going to come up with priors? You could come up with different reasons for coming up with different priors. But if you were to draw a prior like that for everything, and put a little bit more weight over here than there, you would need a reason for it. So, and maybe there's something contextual about the problem that you know. And you're like, no, we know it decays at least in some way. Maybe we don't know it decays exactly like this, but this is a starting point. You're going to need some reason. The way I phrase the problem, I don't have any reason for doing that. So I like the flat prior still. If you wanted to take this problem and also learn P, you have an opportunity to do that. I would agree, you probably need more samples. How would a Bayesian change this problem? They would just put a prior on P. You'd probably use beta half-half. So multiply that one in and come up with a joint posterior of the theta and P. And you can start thinking about in the context of confidence, how would you come up with a confidence set that covered both of those? And that could be pretty tricky. But for a Bayesian, likelihood function, just write it down, it's got the info in there. So that's not something that anybody just created, it's something somebody did and it seems like a good idea. If the likelihood has all the information about the parameters and how they relate to the data, the sampling distribution has that information, that same relationship is encoded into the likelihood. So why wouldn't you use that? And that's what it is right there. So it seems to be a good idea. The second case right here is x1 is different from x2. So this doesn't give me too many options right here. So this is a 6 and that's a 4 right here. They're different from each other. That's the constraint on the problem. It's a good thing that constraint is encoded into this. I get to know the process. So, and I do this. I got a 6 for x1. So this is going to be a 5. And this is going to be a 7 right here. And then I've got a 4 for x2. And this is going to be a 3. And this is going to be a 5. And look what happens to this function right here. When this is a 7, this is a 1, but this is a 0. So this whole thing is a 0. And if this is a 3 over here, this thing is 1. And that's a 0. So that's a 0. But when I'm old, it's 5. They both agree, and my posterior distribution looks like this. So at 5, my example, and I guess the way I thought about this, I put that at 1 kind of arbitrarily. It's just the way I like my switches to work. And that's already pre-normalized for me, so I could ask the question, how do you normalize that, but you're already there. And it's telling you right what you think you should know. So again, likelihoods are doing all the action here, which is kind of cool. But we did want to at least understand what influence the prior could have. I really like this problem because you could take that extra step and start inferring P is a Bayesian. And I use the exact same work I've already done in terms of the theta, and I just open up P as a parameter, and I slap a prior down on it. So I've got a process that I can follow. We're not going to do that analysis because we have to understand what that joint looks like. But conceptually, you could imagine how to do that. I mean, you could come in and say, I'm going to hone in on a chunk of this space and try to tell you about the densest part of the space. So let me finish up this story and tell you the many different ways that Bayesians can make intervals. So this problem had to do with sets. Let's just go back to more of a continuous density, so not point masses. Because point masses, I think you know where you would end up telling people the answer. If you had some big point masses, tell them about them. You had little tiny ones. Well, if those are big compared to much, much smaller ones, tell them about those too. And take ratios of those probabilities and tell them about those ratios. So tell us, this one looks 5 times better than that one. Things like that. So I think everything is relative, but how you report the answer is up to you. So back to intervals. And Bayesians call these credible intervals. I've always wanted to know the story on this word coming up. Where did it come from? Who did that? And I still don't know. So it's obviously just a little joke back to the frequentists that were coming up with coverage sets, and they're like, well, we're not going to to use the probabilities word, we're going to change the word. We're going to say we're confident. And confidence is a statement about process. So not about your actual inference at hand. In some cases, they might be really inferential intervals. But I would say the 75% statement here is just a statement about process. So Bayesians have their own word, and they like it credible. And maybe that was humorous to somebody once upon a time. I'd love to know what that story was. Let's imagine you have a density. So Bayesian is going to construct a interval for a density. And if you have a density that looked like this, symmetric, you might be thinking, oh, I just want to grab the tails of this thing if it was symmetric. So you might end up looking at the 0.025 probability in the tails. So that's going to be my mass right there. If I add these up, it's 0.05. And this is going to be 95. So these are just called symmetric intervals. If you have a Monte Carlo procedure and you're collecting all of your data, all you have to do in one dimension is order everything, all your samples, and then take the 97.5 quantile and the 0.025 quantile, and that will define the interval for you. So very easy to do computationally. And I would say in this picture right here, there's no argument. Everybody's going to want this thing. But I can draw a different picture. So let's imagine a different interval. And I could either do this bimodal or skewed, and I think the result is the same. I'll choose to draw this bimodal. Same issues would happen. If it was skewed distribution and it was heavily skewed, chopping off the symmetric tails might not be the best interval. You'd still say that's a 95% interval. Let me draw a picture over here. Say I had a distribution that looks like this. And I go 2.5%. And I say, ooh, 2.5%. And here, this doesn't look great. I say right here. And that has 2.5%. You say that looks bigger, but I say, oh, that's coming out for a long ways right here. So that should get that thing out. What's wrong with this interval? It's got 95%.
It's not centered at the moon.
It's not centered at the mode, that's true.
Spans a large inference.
Yeah, it probably is too wide. So this is wider than you might want. So let's say too wide. We could come up with a different interval that's shorter. This is true for confidence intervals as well. So there is the length of the confidence interval, and you want the shortest one. And they never taught me about that in undergrad classes, but I did take some grad classes where they said there's ways to do it, and it can be difficult to construct the shortest interval. So conceptually for a Bayesian, it's a pretty easy thing to do. If I chop off the 2.5% tails right here, and let me just make it even more ridiculous, and have that thing come way down here. And I said, oh, and I'm going to make that thing like 0 right in here, just to make it super ridiculous. And I say, oh, I think the answer is in here. 95%. That would be a correct statement. I believe it's in there. That's where I think. But I could come up with a shorter answer and restrict our attention to different things here. And here's how we do this. Is conceptually, what we want is the shortest interval. It always contains the same amount of mass, the 95%. So if it's short and it has the same mass or the same volume, we might say that's very dense. So these are called highest posterior density intervals. So HPDs. So highest posterior density. And this is a synonym for the shortest interval that you can get. Here's how I do it. Start with a line conceptually at the very top, right here. And I look at how much mass I have contained underneath this line. So when I add it all up, and the way I've drawn it is it's got all the mass. So if this was normalized, it would add like 1. So if I added all the line area under that, let's draw a more interesting line where I start cutting through the density. Right here, I have all of this mass in here, and I can add that up to some number. Let's say that that's like 62% of the mass, and I want a 95% interval. Why would I want a 95% over a 62%? Why not a 92%?
Kind of arbitrary. You can have 62%.
It's not just kind of arbitrary, it's bizarrely arbitrary. Everybody rounding to 5s and 10s. It's not super arbitrary because it's the way we count, but if you're making your decisions just based off of this arbitrary stuff, it's pretty silly. I would agree, I want the probabilities to be high of something, but I like 92s. So, especially in a Bayesian sense, if I thought something was 92% sure, that's a totally different statement about error rates. So we'll go through that when we get into hypothesis testing. I keep lowering the line, so here's my algorithm. I'm gonna lower the line a little bit here. I just collected a lot of mass. And then maybe I added up with both of these that I got an 86% interval. And then you keep lowering it incrementally until you get everything. And then maybe I've got all of this mass in here. So I'm adding everything, even the stuff above the line. The line is telling me what to add up. And this is actually how I coded this up once upon a time. Exactly like this. I was working in like a 4-dimensional problem, and I wanted the highest density set. And I wrote a piece of code to basically gridify my big density in 4 dimension, add up points on my grid, and I was lowering this hyperplane over it, and checking to see if things were inside boundaries, because it was a multimodal thing, and maybe I'll present that code to you eventually. Now they have better code than the one that I wrote. So conceptually, this is an easy idea. In high-dimensional spaces, you can code up that thing. But it's a computational burden to do all that. And so in a lot of problems, you often do just do the chalk to 95, chalk to 2.5% tails, if you think it's roughly symmetric. What you're doing is you're trying to characterize behavior of the distribution. So what's the right characterization? If I see a bimodal problem, I want you to tell me about both modes. I want you to tell me the centers, I kind of want you to tell me intervals around them. But there is no rule. This is just conventions and what makes sense. So if I had a heavily skewed distribution, I had to tell somebody it was heavily skewed, I wouldn't be describing it right. HPD might help you with that, but then also where the mode is would probably help you. So all of those summaries. You're allowed to summarize how you want. I like intervals better than I like variances, but I see Bayesians, they run all their stuff, they've got this crazy posterior, they've got all kinds of information, and they report the mean of the variance. You know, and it's like, yeah. So sometimes people show each other contours so they can see relationships, and I think that's up to you. Humans are not great at processing high-dimensional information, but if we can summarize in interesting ways, and I think that's a lot of Bayesian investigation. I've got my posterior now, what's interesting about it and what does it all mean? So, and that's another layer of investigation. So that's intervals and sets and coverage. So conceptually easy, but I think very complicated for people when they first learn about it because they don't have counterexamples. Chris?
2 questions. Is HPD always the shortest?
Yes.
And is that approach where you drop the line always the HPD?
Yeah, so if I take something, and it's the way density works. It's because we're always adding that function up to 1 that it'll give you the shortest interval. So what is it grabbing at first? It's grabbing the tallest stuff with the most probability. So it will add the probability fastest and give you the shortest interval. You could probably even come up with a little Riemann sum proof, or if you said, yeah, that makes sense. That's good enough for me. But you could prove that with rectangles.
But you mentioned the software does things besides this approach for other reasons. What are the other reasons that this is always shortest and always
speed? Computation. So I write something, I've got a 9-dimensional inference and I want to do this. Now you've got a problem. So if you're running an MCMC, you're not getting back the density function per se. You're getting back a ton of samples. So what do I drop the plane over? Do you have any ideas?
Well, I see how that would be like computational inference.
Yeah, well, what are you actually coding up and dropping the plane over? You've got these frequency counts, and usually in a continuous problem, none of the two numbers are the same in there. So what would you do?
Kernel density.
Yeah. So you have to do a histogram, basically. Histogram would be just flat basis functions. If you were in college again, they might teach you about using parabolas to model shapes of things. They built Simpson's method out of that. But we use densities. So we'll use little normal densities and put one over each data point, and that's called a kernel density estimator, kernel smoother. So we'll come up with this smooth sort of thing, and it works great in 1 dimension. And as you move to 9 dimensions, they work really badly because using that bin width is like difficult to pick, so bandwidth selection is how wide those low normals are. And in high space, most of your space is empty. And so you need adaptive bandwidth in high space. So I convinced myself in graduate school at some point to never, ever, ever do a KDE estimate if the dimension is high and my breakpoint's like 7. I just don't trust that they work very well at anything. I do use them all the time in 1 or 2 dimensions. But in high D, it's so cumbersome to work with those things. And you have to build a KDE to smooth it out and then drop the plane under your KDE or something like that. So there's these steps. So conceptually easy when I draw a curve on the board, but if you're running a big MCMC in high D, probably not going to do that. Saying that, I don't know if anybody that thinks about these boundaries in 9 dimensions, you know? So, and that's a pretty low dimensional number in, you know, with respect to the analyses people do now. So you might pick out pairwise dimensions, and I'll try to look at what do the contours of the distribution look like 2-dimensionally, and plot contours for people, and they can look at and that's usually what people do. It's hard to look at things over 3 dimensions. But you look at a bunch of scatter plot contours of the distribution, you could look at that and give people 2-dimensional boundaries for everything, but you're not giving them the full high-dimensional thing. If you were building a machine learning algorithm that was trying to give you the best prediction ever, you might want to invest some effort into getting that 9-dimensional boundary right. You probably, my opinion is, in real problems that are bazillions of dimensions, you search over all the dimensions, but at the end of the day, it's like a dozen of them that are telling the whole story. And your investigation is to cut through the weeds. So, lots to think about, but there's no hard rule to this. Shall we switch the page and jump into a new lecture? Let's do Poisson real quick. Let's spend some time doing Poisson, and then I'm going to try to get us into MCMC as quickly as possible. So I just want us to relax and see that we know how to do this stuff. Different problem. We'll spend a day or so on this, day or two, and then I'm going to jump into Monte Carlo. If you want to look up the RAP paper, the Gelfand and Smith RAP paper, it's on the website, so just scroll down it, same column, it's a link there, open it up, and just turn the page real quick. And go, okay, there's this paper, and it's got all these correlations, and it's got all this stuff that they're trying to model about some rat experiment. Maybe just read the abstract, but it's really going to set you up to learn about Gibbs sampling, and that's the example I'm going to use to teach Gibbs sampling. It's actually the original example that Gelfand and Smith worked on. So I like to do it, and because it's so arcane now, it feels so old. But it's kind of cool that this is where this stuff came from, and I'm gonna give you guys an opportunity to criticize this paper.
What's the, where do we find it?
Bayesian Statistics on the webpage, on the schedule. It's the class schedule. You can look at that. I mean, we won't talk about it probably until Wednesday. That's just what's coming. I'll teach you about Wishart distributions, and then I'm going to bury all that lecture into big MCMC lectures. Eventually, I'm going to have to code that paper up. So it's just kind of fun. I'm going to ask you questions like, are the priors reasonable? And you're going to have different answers to that question. I think that's the conversation that we want to have. Let's sympathize with Gelfand and Smith in advance and know their interest was in concocting MCMC algorithms. Bless you. So I think they didn't care about certain things in that paper, and we'll pick on them for it, but we'll also look at their huge contributions that they made. And then I'll show you the paper that they eventually wrote, which is much better. Okay, let's just go to Poisson distributions. Let's do Poisson inference. It's very similar to all the stuff we've done before. So I first have to tell you what a Poisson distribution is. Poissons have a random variable that counts stuff. Dot, dot, dot. These are just counting numbers. If you insist. So that's how we count. Make us look a little bit more mathematical if we're not just doing that. So what does this distribution look like? Does anybody know? That's the easy part. Can't forget that. Lambda to the xi, I'll say there's no I in here. So x factorial. So this is it. And I was extraordinarily excited when I first saw this. This parameter right here is a number that lives between 0 and infinity. Now I want us to just think about what that parameter actually represents. So what do you think when you look at this thing? What is that parameter doing? So Dylan interprets it as moving the mass around. So he's almost setting us up to think of it as a shift parameter. There's things that you can know about this, and this is something that Dylan knows. Wow us. Lambda, good job. So, not Dylan. Lambda. Good job. This one's kind of easy to remember. I love this when I first saw it because I barely learned about what a Taylor expansion was. The first Taylor expansion I ever learned was E lambda, not E negative lambda, but E lambdas. And that looks something like this stuff, you know? So that was the Taylor expansion. So if you ended up summing over all of this stuff right here, it would sum up to E to the minus E lambda. That's the normalizing constant. So I was like, I already know what a Poisson is. Never even seen it. That's cool. I wonder how he came up with that. And then we learned about how you derive a Poisson distribution. Just a few more tidbits. This is weird, right? The expectation and the variance are the same. Does it even make any sense? Like if you were counting that this is sensible? Roughly sensible?
I would think you're more likely to make more errors than when you count.
Yeah, exactly. So if I throw down two things at you and I say how many are there, you can distinguish 2 or 3 pretty quickly. But if I ask you to make lots of counts and count things for a long time, probably still make some errors. So I would probably agree variance should be climbing as that's getting bigger. We could prove certain things and say it's not possible for any sensible counting distribution to have lower variance than the mean. And there are things you can do in advanced inference classes where you can prove that that really is not a possibility for you. It has to do with exponential family stuff, but I would say this, if you ever see variance that's less than the mean, it's because you have a mixture of Poissons. So, a Poisson over here, and you have another one shifted over here, and you don't know which one you're getting things from. And so, that can drive that sort of phenomena. So when I see variance less than means, I think that's probably a mixture of counts. Things like that, and I need to use Poissons. I do think this is a pretty harsh constraint right here, that we probably want some flexibility in here. But back to our original question, how do we interpret this parameter? Dylan, like a lot of people, likes to think about means first. So he says, oh, that's like a shift, but it's not a shift, right? That's not what this looks like in this thing. The x's and the lambdas would have to be separated by a minus sign in here. So it's not a location parameter, but it certainly is adjusting what the location is. Keep in mind, we're bounded by 0. So if we're yanking out the scale of the distribution, the variability, we're naturally pulling the mean in a counting distribution, and that's something that you would expect to happen. This is like a scale parameter, is the way that I would interpret this. So I would start thinking about it, it's looking a heck of a lot more like a scale. So I always think about variances before I think about means. I don't know if that's true, but I have adapted myself to think about uncertainties and how things fluctuate more than just what they look like on the surface. I could probably write the next book about that. So there's all kinds of metaphors there. Anyway, I think of it more like a scale parameter, but obviously it's got kind of this mixed meaning, which is kind of fun. Here's some facts. Fact, I'll say if x is binomial with two parameters n and p, and n gets big, and p gets small, this is not enough for these things. There has to be something about that. N can't get big too fast compared to p. We also need np to converge to something. And it will converge to something, a constant. And we're going to call that constant lambda. This process right here in the limit converges to a Poisson. So it's a rare event sort of model you can think about. So we're not going to prove this here, but it's in probably your elementary probability book. It's in like baby loss book and things like that. It's definitely in Cassell and Berger. So this is about the second thing they told me about Poissons, and I thought that was cool. And I had a lot of people over the years start saying, well, n's big, p small, Poisson. And I've seen this done a lot, Poisson, boom. And that's not enough. So there's something here about this. It's hard to check with actual data, but that's easy to check. So I've seen people model things with Poisson where that's like 5 times the size of that. It's not Poisson. It's some other distribution. So, and if that's ever lower than that, it's probably a mixture of some other distributions as well. And so that's not the only thing, but I would say this is the fundamental counting distribution. And I can do all kinds of stuff with this distribution, like I can change a normal into a key. I can also change Poissons into other things. So let me just show you other counting distributions. And this is how Bayesian might model things. They might start saying, well, I got counts. I'm going to call it Poisson and see how badly I do. And I like to do that. I like to fit things, look at residuals and go, where are all the residuals here? And that's the interesting part to me. So almost like control systems. This is a mixture of a Poisson. So it looks like this. So I'm going to just have whatever this distribution is, probability of x, Given lambda, keep in mind lambda is continuous, so I can integrate over it. The x's aren't continuous. But I could do stuff like this, where I could end up putting a distribution on lambda. And I could mix over that. And I can integrate between 0 and infinity. And this is some other distribution. And you could probably convince yourself that if you did this right here, you're adding extra randomness lambda, you might keep this centered the same if you multiplied by something that was on average 1. But you would change the variance and blow that out. And you could change this constraint and make whatever this new distribution is have greater variance. And you could fiddle around with that thing, and there's different ways you can do that. There's one specific case where that's a gamma. And there's two parameters right in here. If I picked alpha is equal to beta, I'd be multiplying by something that's on average 1, and I wouldn't be changing the location of everything, but I would be changing the variability. And if you do that, the resulting distribution is a negative binomial. And I'm going to tell you about those next week. So I'll give you a little primer on negative binomial distributions, but I just want you to see up front there's a connection. So going back to our normal distribution, when I mixed over the variance parameter, I turned it into a t. And that's what we did. We did something more like this, where I have a lambda, but I multiply by maybe a gamma, and I change that to gamma. So I might want to preserve that to have the same meaning as before, and I did something like that to the scale parameter in a normal and turned it into a t. So these are called scale mixtures. So this is a scale mixture. And that's what Bayesians do with all their stuff. They get all these distributions, you don't like the way everything's fitting, you do something to it. So variance is too small. So now I'm going to find a prior, or at least this mixing distribution. I don't even have to think of it as a prior, but if you're used to priors, it looks and feels like one. Then I can just mix over this thing and I can come up with a new distribution by talking about old distributions that I used to know. I get something fancy out of it. And sometimes we know the properties of them. So I can come up with an infinite collection of counting distributions by considering an infinite collection of distributions here where they're just positive right here. So they have positive support, and the reason it needs positive support is because that's what that means right there. Very typically it's gamma, and it's a question of which gamma would you use, which alpha and beta. So that would be a good starting point. We'll learn about negative binomials next week. That's actually going to be our predictive distribution for everything. So you probably already figured that all out because you've been asking yourself the whole time, what's the conjugate prior to this? And then you thought, oh, I'm going to formulate the predictive distribution in my head because I'm going to do the posterior analysis. The conjugate prior is something I know what the posterior looks like. It might look like something here, and I can apply it directly here. So if I understood this rationale right here, then I know what the forecasting distribution looks like. Even though the way I conveyed this information is a totally different topic. And it's the exact same math. We'll break that down slowly next time. But let's just answer the question, what's the conjugate? The conjugate prior. Yeah, not all at once. So I'm imagining myself that everybody knows the answer to that by staring at this thing, and they didn't want to say it. I didn't want to. But I appreciate the guys that did say it. They feel like a novel. So it's gamma. I can just check if I multiply by gamma right here. This is going to look like alpha minus 1, lambda, alpha minus 1, e to the minus lambda beta. I can multiply that into that, and I'll get something back that looks very gamma. we'll do that. I want to do a sanity check and look at the mean and see if it makes any sense whatsoever. And then I want to talk about how to pick alpha and beta. But you're probably thinking you're going to limit them, just like we did with the precision parameter. If that's what you're inclined to do, that's what I'm inclined to do. So I'm going to limit them both to 0, and the resulting product that we're going to get is alpha and beta both go to 0. This is going to be converging to 1 over lambda. And no surprise, this is going to be better. And in the first week of class, that bothered us, but we're starting to like our answers. So I do think there's something to be said for the answers are compelling, but there's other ways to think about it. Let's do that next week. About 15 minutes of pretty easy stuff. And then I'm going to introduce you to the real world distribution. I guess if I do the full-blown integral on the board, it'll take all lecture. And I'll say I'm 75% sure I'm going to do that one. Okay. So probably the integral. So buckle up for that, and you'll be a little bit relaxing. Thanks, you guys. Have a great weekend.